Thank you. Welcome, everyone. I'm going to present my semi-offline attack on Android full disk encryption. This is who I am, Oliver Kunz. If you want to contact me, that's my Twitter handle and LinkedIn. I studied my MSc in Information Security at Royal Holloway. Beautiful school down there. If you have seen Age of Ultron, you probably know the building. I must say many thanks to the university and especially Professor Keith Martin, if he ever watches this online. He was a great help during the process of my master thesis. What I will tell you is some parts of my master thesis. Unfortunately, I don't have the time to go through everything, and so I will focus on 3 types of attacks. First, to give you some introduction into Android and full disk encryption, and then we cover the baseline attack, the baseline for the benchmark, the online attack. You will see it's quite the obvious one. The offline attack is also quite well known. It's an attack that was previously presented by different speakers and discussed online. And then comes my semi-offline attack. All 3 kind of attacks are brute force attacks. And brute force, all the scripts are proof of concepts, the stupidest, most simple brute force strategy, 4-digit PIN, start at 000, run up to 9999. So you can increase a lot of efficiency there, but that was not the point. It was the point to prove that something is possible. Right, let's jump in. So in full disk encryption, we have the situation that if you lose your device or someone steals your device, you would like them not to be able to access your data that you store. That's why you have this full disk encryption. To control encryption at rest, I hope every one of you has heard this term, has the problem that as long as the device is running, this encryption is transparent. How many of you actually shut down the smartphone? I don't, but it's still there, probably for marketing reason, I don't know. If I have the device as an attacker, I can do much more than just look at the ciphertext. I can attack the ciphertext, I can attack the cipher, I can attack the whole crypto system. I can do whatever I want. I'm in possession of the device. Let's assume I won't give it back to you, right? I'm not a nice guy. So the elements of full disk encryption is, obviously, we need the data in the disk, but forget about that. We need an encryption key. Android calls that master key. And we need an encryption cipher. In Android, that's AES-CBC. And somehow, we need this process of encrypting and decrypting data. And for those of you familiar with Linux and full disk encryption, notice this is decrypt. And that's exactly the thing that does for every read operation, it decrypts the data, and for every write operation, it encrypts the data as long as the device is running. So it is a transparent encryption. If you have access to a device which is encrypted, and it doesn't prevent you from accessing the data else, like the screen authentication, you have access to the encrypted data. But if I ask my mother, please remember at least 128 bits for the AES key, she will say, are you stupid? Right, and she's probably right, because let's face it, 128 bits. So that's not a good idea, we need something else. And what we need is a key encryption key. That introduces sort of key hierarchy. The key encryption key encrypts the master key. But we still have the problem. To sufficiently secure the master key, we need another 128 bits. Right, not really helpful there. So that's why we have password stretching or also key derivation functions. We use a user-defined value, password, PIN. Most users really bad at this. And try to create a cryptographic key, which we then can use to encrypt the master key. This allows us, the user can change the PIN and password, it changes the key encryption key, and this just re-encrypts then the master key. Let's have a look at all these different things, with exception of decrypt, because of the time. AES, I hope every one of you has heard of that. It's a block cipher, 128 bits block size. Android uses the lowest key, the 128-bit key. A block cipher runs with sort of mode of operation, CBC, also something I hope you have already heard of. It's probably one of the most well-known mode of operations. And an alternative mode, which was designed by IEEE, and this is standard, is the XTS. What XTS stands for is this long string down there. You can read it yourself. I saved this time for me, actually. It's there in Android, but you need to change the source code. You need to recompile the source code, or you ask a manufacturer to actually do that for yourself. But it's not the default value. That's why we look at AES-CBC. It's used for encryption, and it's also used for building other crypto primitives, like the CBC MAC. How it works is, you see it probably here best on the graphic. You chop up the plain text into 128 bits blocks. And then you XOR the plain text block with a previous ciphertext block. That gives you an issue for the first plain text block. That's why you have an IV. And then you just do that until you reach the end, which is very nice if you send your data from A to B, because this mode of operation is self-synchronizing. You don't need to synchronize a counter or something else. You just send the data, and it works. But when we think about the disk and we want to encrypt the disk in that way, that means, let's say, 100 gigs, chop it up into 128 bits blocks. Then we start encrypting with the initialization vector at block 0, and we go up till we reach the end. And now I want to store something else on the disk, on, let's say, plaintext block 2. That means I have to decrypt from the back down to block 2, change the bits, and re-encrypt. Done. That's very inefficient, right? I mean, we don't have that much of time if we want to write something on the disk. So we needed something else for that, and that's the ASS-IV. It creates a per sector IV based on the sector number and the master key. It's a cryptographic function. It gives you an IV which fulfills the properties up there, and that's very nice. Now you only have to decrypt the sector, and you re-encrypt the sector if something changes in that sector. Probably one of the most important things, the master key. In Android, the master key is generated with that function, encryptfsc. That source code file, if you ever want to have a look at Android full disk encryption, start there. It's sort of where everything happens, more or less, or everything else is called. What this function does is pretty simple. It reads from def-u random twice 16 bytes, which is 128 bits. Those values are static. If you don't wipe your phone, those values stay with your phone. As I said earlier, it's protected. The master key is protected by the CAC. It's another AES-CBC encryption. And the encrypted master key, along with the salt and other values, is stored in the crypto footer. The nice functions that let our users use some rememberable password values, KDFs. Two functions here. Password-based key derivation function 2 is also an older, well-known function. It was used in Android until 4.4 to derive the CAC. It's not used anymore. The issue with PBKDF2 is it's only CPU expensive. And who has a gaming PC at home with a nice GPU, right? It's basically done. So there is a new version now, a new KDF, and that's used in Android 4.4 upwards. It's Script. Script has the advantage it's not only processor expensive, but it is also memory hard. So for the same operation that normally you would write something which takes less memory, it blows up the memory quite large. They are designed to make brute force slow down the brute force, and create a cryptographic key. That's their task. And you see in Script, PBKDF2 is still an Android because it's a building block. It's a set of algorithms, and one of the algorithms is based on PBKDF2. What both functions have in common, they have tweak values. So with increasing processor power, increasing memory we can also increase the cost of these functions. And the user, when he just enters a PIN or password once, is not significantly slowed down by that. But if you do this 100,000 times, yeah, you really get the timeout. Simple application, pin password, apply the KDF, and we have the CAC. Now good, I told you about full disk encryption, the elements. Let's see what is actually encrypted. For every Android device or Android version, Google releases a CDD document. And in the CDD document, you have all sorts of things that manufacturers need to, must not do, should do. And in Android 5, it says that the user data should be encrypted, the user data partition. That's /data and every non-removable internal SD card. And you need full disk encryption as a manufacturer as soon as you offer a screen unlock. Good, we have that on the smartphone, right, both? User data is encrypted. With Android 5, they said you should encrypt the device on the first boot. That gave some backlash for Google because once they said every Android 5 device should be encrypted out of the box, but in the CDD it was only written should, so big manufacturers ignored that for the time being. So it's not the full disk, right? It's only the user data partition. The system partition is not encrypted. Does it have to be? Probably not. It's public. You can compile it yourself and you know what Android is, right? So it should have an integrity check, but that's another chapter of the book. And we need another important partition here for these attacks. That's the metadata. It's where the cryptofooter is located. And the cryptofooter, as I said it earlier, holds the encrypted master key, holds the salt, holds KDF parameters, and all other stuff that you need for the full disk encryption. We're down to the first attack. We are building the baseline for our benchmark because we need something to compare against. Those are the conditions for this attack. For as long as it takes to enter the PIN on the device, I need access to the device. If the device is lost or stolen, that's no big deal, right? I have it. You can either do that by a brute force script, like I did in my work, because I didn't want to do the physical attack machine, which Engler and Wines did. It's one of these nice robots where you have those you have in the chip factory, which go around and position the chips. Really nice, costs about $200. Didn't have the time, didn't have the money, and I'm not a robotic engineer, so stop that. The script would be prevented from execution because ADB is disabled and ADB needs an authentication. So I accepted my attack host on the device and enabled ADB by default. And then I have two methods to enter the PIN. I can use input tap, which simulates the user tapping on the screen. I need to map out the keypad for that one. And since the Nexus 4 is smaller than the Nexus 6, I had to do this twice. But then I was looking around. I didn't do it a second time, actually, because I'm lazy. So I was looking around first, is there a better option? And I found input text. And hey, it's not just more convenient because I don't have to map out the key layout. It's also just sending a string to the device. And it's much faster, right? So good, more efficient. We have a very lousy brute force strategy, but I can save some time here. And then I needed something to actually recognize if I found the correct PIN. And for that, I run ADB dumpsys. That's a tool where you dump out system information, and there is a string mlock screen shown. 10,000 pins, almost 23 hours. That's a long time. 2,000 timeouts triggered. Yeah, and only for 10,000 pins, right? So we don't have complex passwords, but hey, who is using complex passwords in the phone anyhow? We have actually two different prompts, and that's interesting. Now, look at the table. We have a startup prompt, which is where you enter your PIN and you use the KDF to derive the CAC. And we have the screen unlock, is when you lock the screen and you actually want to access your phone again, you enter the PIN. Both times it's the same value, but the countermeasures are different, much different, especially if you look at the action row. If I enter the pin 30 times false in the startup, I have a wipe. The data is lost. In the screen unlock, I triggered over 100, over 2,000 times the timeout, and there was no action, no final penalty. I would say probably there is none for that, really. Or I said of the 2000s, I assume it's none. We could secure that a bit in a more efficient or more better way. Increase the penalty timeouts, actually make it variable, so that it's not all the time 30 seconds. So once it's 5 minutes, once it's 10 minutes, an hour, you get. Or we enforce the device wipe after, I don't know, I think 2,000 failed attempts, it's quite enough. Even if you have a toddler who likes to play around on your phone, don't give them your phone then. It's probably the thing. But it's important to know it's the same value, and it's quite important. It's an important value. But once it triggers the final action, and once it doesn't. So this is my conclusion for the online attack. ADB is secured sufficiently enough, so you need a physical device. Physical device is, well, for the PIN, probably easy to create, but for pattern and passwords, you get it. It gets more and more complex. Time cost, almost a day. Yeah, that's okay. It's quite long. But I missed some security controls. We could still improve that. So we have the baseline. Let's go to the second attack. Here we have the following preconditions. I don't need the device for the full brute force attack anymore. All I need is to take the user data and the metadata off the device. So I need access to the device for as long as it takes to image those partitions. And then, as the name says, you run the attack offline, off the device. So I'm now the attacker. In the best case scenario, there is no locked bootloader. If you have an unlocked bootloader, lock your bootloader. I just boot the recovery image and look for where the partition is residing and image it with DD, send it over to the attack host with NC, and it's done. Quite straightforward. In the worst case for the attacker, he has a locked bootloader and ADB is disabled. Well, unlocking the bootloader triggers a device wipe. Simon and Anderson figured out that the device wipe are faulty sometimes. It was mostly for older Android versions. And they also said full disk encryption could help with that one. But they also said they found enough material with full disk encrypted devices that potentially leads to decryption of the master key. I just assume they may have found the crypto footer, but yeah, you get it. It's an issue that we have there, but something else we need to figure out. But as an attacker, no, I don't want to gamble here. I want your data, so I'm not doing that. Instead, I use the JTAG interface, which probably almost any device has now, or still has. You can read this article about how to image through JTAG. And last but not least, not on the slide, unsolder the chip. That's quite complex, but still, that's your last resort as an attacker if you want to image the device. So there is an attack script already there, written by Cannon and Bradford from VIA Forensics. It now ships with Santoku Linux. I actually used a different version, the one that the author from Android Security Internals, Nikolai Alenkov, made some additional changes to. It's, as I said, also just proof of concept, following the same brute force strategy like all the other scripts, running from 000 to 999. How does it work? Simple. I take a candidate pin, apply the KDF, decrypt the master key, decrypt the header file, check if it's actually decrypted. This one is my inclusion in that script. Check for the X4 magic signature number. Before that, it only looked at offset 16 to 32 if there are 16 null bytes. Should be with X4, but you know, it's kind of a poor man's solution. We have a signature here, so I do now both checks. And when I found it, I found the pin, and when I found the pin, I can decrypt the master key and the whole data. That's the script, how you call it actually. The header file is at least 1088 bytes. The footer file is the complete metadata partition, so the complete crypto footer. And guess what, how long it takes? 51 minutes, not 23 hours anymore. Yay! No applause? Come on. It's not my attack, but still nice, right? That's during my master thesis, one of the tests. It took quite a while, so that's why I didn't run it today. Yes, that's my birth year. Yes, I'm not using that anymore. But many people do in 4-digit pins. They use their birth year or use their zip codes or whatever. So that's how you can make your brute force strategy more efficient, by starting with those numbers. But still, it works. 51 minutes, not too bad for the whole pin section. The countermeasures, I said it earlier, hopefully we have a locked bootloader. We certainly have disabled ADB, and we have ADB authentication. That's on the device where we can try to prevent the imaging. Off the device, all we have is how strong the KDF is and how weak the attacker's host is. And that's just a matter of time, a matter of power. So here the conclusion to the offline attack. Well, we're more efficient now as an attacker. That's not good. We're missing some security control here, so we don't want this attack to happen, right? Even though the last resort is unsoldering the chip, it's still not good. We, and actually Google as well, has acknowledged that imaging a partition is possible. How they have acknowledged it? It's good news. They brought some improvements in Android 5. And that triggered me. That is what I wanted to see in my master's thesis. Does it work? Does the offline attack not work anymore? So that's where I started. Let's look at the improvements that Google gave us. They call it hardware binding of the encryption key material to the device. Sounds nice. That actually means you need the device which the encryption happened to decrypt it. In the best scenario, it means you cannot get the crypto filter off the device, you cannot get the user data off the device, and you cannot run it off the device. So the offline attack would be prevented. To be clear, it's not the master key that they bind to the hardware, it's the key encryption key. The master key is still the same function, read the 16 bytes from the FU random. You also do that on the first boot when you have Android 5 default encryption on the boot. Think about yourself, what that means, the FU random from boot, reading 16 bytes twice. But let's look at what actually changed, how the CAC generation process changed. That's still the old one. We have the PIN and password. Previous to Android 5, user could only use those two screen lock methods. We have the KDF, which is applied to the value, and then we have the CAC. Well, that's the new one. Looks a bit more complex, a bit more signs up there. First, you notice it's not just PIN and password anymore. We have patterns. That's nice, good usability. Default underscore password, yes, that's a string, and yes, that's there in the source code. Because when you encrypt the full disk on the first boot, your user hasn't had any chance to enter a screen lock value, so you need something to derive the CAC from, and that's the default password. You apply the KDF, now you get an intermediate key, not the CAC anymore, the intermediate key. Next operation is sign this intermediate key with the key master trustlet. The key master trustlet is an application that runs in the trusted execution environment of your system on a chip. So if you're running a Qualcomm SoC, it's the QSEE. You probably have read that in the past weeks because researchers are actually looking at the different APIs of the different trustlets there. The key master is one of which. It has an internal key. That's important to note right now, but let's look at the signature key. That's an RSA private key we use to sign the internal key with the key master. Because all the information about the crypto of the full disk encryption is stored in the crypto footer, the signature key is also stored in the crypto footer. which is good for me as an attacker, which is not so good for the device, but it's protected. It's the private key. It needs to be protected, right? And the protection is an internal key in the key master that encrypts the signature key. And that's actually the hardware binding. It's not really down here. It's up there. But that happens now, so I need the internal key master key to decrypt the private key to sign the intermediate key. Good? After that, I have the signature, we apply again a KDF, and we have the KEK, and we finally can decrypt and encrypt the master key. So quite complex if you compare to this one. But is it sufficiently enough? No, because that's why I'm here. So let's talk about my attack. You see, it's not offline anymore, it's semi-offline, so you probably get the hint. These are the old attack preconditions from the offline attack, and just look what changes. Yeah, we know that sentence, right, from the online attack. So still, it's not a big deal, because I've stolen your device, I found your device, and I still have to image a partition, which is also not a big deal. I still can do it, last resort, remember, unsoldering the chip. It's a bit nasty with that attack. You would have to resolder the chip afterwards. So more complex, but not impossible, I guess. I needed a new application, and I needed a client-server application, because, hey, it's semi-offline, not offline anymore. We have the server that runs on the device. That's why it's not offline. It's based on the crypt FSC, because I don't want to write all the code which other people have already written for me. It's also based on the offline attack script. Had to change there quite a lot, actually. They communicate with each other. Obviously, it's a client-server application. One runs on the host, one runs on the device, and that's their tasks. In the client, you see, it's basically all that you also have to do on the offline attack, or what I had to do on the online attack. All these kind of steps. Process the crypto footer, run the strategy, perform the KDFs, decrypt the master key, decrypt the header file, and check if we are actually successful. On the server, I needed to find a way to initialize the key master with the RSA private key that I have imaged off the device. So I found a way to do that. Tick, one step closer to the attack. Then I needed a way to get the key master trustlet to sign my value that I send him. Could do that, check, good, we're one step closer. And that's the communication, what happens. I initialize the data on the server. Basically, I send the RSA key blob over. Then I generate the first candidate pin, apply KDF on the client, send the intermediate candidate over to the server, and ask for the signature. The server asks the trustlet for the signature, and I send the signature back. And yes, this works. I need to be root on the device, but I have the device, I have the images of the device, so I can get root. And you do that until you get lucky and you have found the pin. That's all it takes at the end. We have the device, we have the application, we have the two partitions. I don't need the device in its original state anymore. I can wipe it, I can do whatever I want with it as long as I don't destroy it. And basically, I wiped it, and I installed a SUA application on it. I got a new master key, I got a new RSA key pair, but I could ignore it because I initialized with the old key material. It's there, I don't care. This is my one, this is my old one. Please use this one, and it works. And this is the steps you have to perform. You push the binary up to the device. You create the TCP forwarding so that you can actually communicate with each other. You start with the SU binary, the POC server, listening on 9999. And I start on the host, the client, with the metadata, which is the crypto footer, with the header file, which is again these 1088 or 2000 bytes. Let's send this to localhost 88. -S oppresses the crypto footer output formatting, because it's nice sometimes you want to look at it, was it actually stored. Minus brute force, 2 hours, 8 minutes. Not 23, not 51, but still 2 hours, 8 minutes. It's not too bad. We will have one slide with the comparison of all results. There you see what is actually the difference. Let's have a small look at the demo, and time is not too bad. This is a demo run that I did earlier this morning. You see on the right-hand side, this is the server running. You see on the left-hand side, this is the client running. The pin is 0800. The master key is there. Have fun, write it down. It's not, I write it in the meantime. It took a bit longer because I reduced the power of my machine for not overheating it, but you get the deal. And this is now the attack that I just run earlier. So what we see here, this is what the server does all the time. It all the time says, oh, I got a new candidate. Oh, cool, nice. Here, get the signature back. At the beginning, I print out the format of the key blob, the RSA key blob that I send out. And then it just waits and answers the requests until it's done and it closes the socket. Here we have the start command. And you see here, just simple, from 000 until you get lucky. Here you see the crypto footer printed out. Yeah, that's it, basically. That's the attack. It's not rocket science when you have seen it, when you have the application. You see the N RMP factor from the KDF script. The script is script and key master. That implies that it uses the hardware binding. We have the crypto type, the AES CBC. And we have the key size, 128 bits. All the information is there. And basically, that part down here, I send over to the server. Not the last one. Yeah. So what countermeasures do we have? Still all the same from the offline attack because, well, basically it is the offline attack. All I did was I took the device into the loop because that's all Google did in their improvement. They just took the device into the loop, but I am the owner of the device. Not the legitimate owner, but I am the owner of the device. They couldn't force a locked bootloader because remember the CDD, this nice document for the manufacturers that tells them what to do and what not to do. There is no mentioning about the locked bootloader. So Samsung gave us a device with an unlocked bootloader, and I really think we are now down to the time where everyone knows lock your bootloader. Even if you hack your device, you want to play around with your device, if you're done, lock your bootloader. You could remove the JTAG interface. That's nice. You will also get some outbursts from the hacking community because we like the JTAG interface. And at the end, you don't really resolve the issue because last resort, unsoldering the chip. But we could also improve a key change mechanism for the internal key master key. Sounds complex, right? We only have one key we can change, and that's the key encryption key. And that changes because the user can change the user value. You can brute force the internal key master key, which protects the private key. I think if I remember correctly, it's 1024 bits. Have fun with that. You can solve the RSA key problem. If you do that, ping me, please. It's nice. And if you can do both of that, you probably can just start brute forcing the AES 128 bits key, right? So solve this work and try to do something else like I did. The question is, when we want to make an internal key master key change, when do we destroy the key? Do we destroy it on user wipe? So when the user or someone else unlocks the bootloader, well, would be good, but if I image the device via JTAG or unsoldering, that doesn't trigger the key change. So it's kind of a chicken and egg question, actually. Let's look at the conclusion for my semi-offline attack. Sorry. Google said they fixed it. I made a cross. Yes, technically they did. And I can confirm you cannot brute force the full disk encryption of an Android 5 device without the semi-offline attack. Just like. But that gives me the actually no. It's not resolved. The base issue here is not resolved. The efficiency, yes, it's less efficient than the offline attack. We'll come to that in the next slide. But the bigger issues are they had the wrong assumptions about the attack. I am in full possession of the device. You lost it, I stole it, I have it. And I can do with it what I want. And they forgot about that, because I can root it. And when I'm root, I can talk to the Keymaster API, which probably I should not be able to talk to when it's that important. So my Nexus 6 has an internal Keymaster key, and as long as the device lives, this key lives. And I have to live with that. I work in corporate now, and we have some nice policy about key changes. And if you work in corporate and you have Android devices, so first of all, you have the master key, which is static, 128 bits. And you have a policy saying you need to change your keys and password every now and then. You need to make an exclusion for that, or you have to force your user actually to do a wipe factory reset of the device, and they won't like you for that. For me, privately, yes, I can accept it. I have to live with that. The key never changes. I was fortunate enough to talk to Google about this issue. Before releasing the thesis, I sent over a small paper to Google, and I was able to talk to the lead engineer of full disk encryption. He confirmed to me I'm the first one who came forward with this attack. Maybe I'm not the first one who discovered it, but the first one who told them. And he also said they're already working on improvements. They knew something like that is possible. But, you know, when you release a device or whatever you do in your work, you never get 100% sure because you don't have the time. So they're fixing it. And it's due to the release in Android N, so should come out this year. I haven't looked at the code yet. I hope I will find the time to look at the code. What they told me sounded promising and complex. Maybe that's why it sounded promising. But yeah, if you have the time, look at it. You know now where to start, cryptFSC. And we have the last slide. Comparison of the attacks. And look at it, 23 hours, almost. The offline attack, almost 1 hour. Mine, a little bit more than 2 hours. Well, now think about what happened. In the offline attack, we have one KDF application, one script. In the semi-offline attack, I have to deal with 2 script applications and a public key operation and communication overhead. And I'm only a little bit more than double of the time. I don't know about you. I call that a success. That's another place for an applause, by the way. And with that, and I think I'm more than ahead in the time, we have time for questions. No questions. One question.
Thanks for the excellent talk. So first of all, you brute force pins, right? So if somebody has a 16-digit password with uppercase, lowercase, and special characters, then those times probably change drastically, right?
Yeah, certainly. So, I mean, those results are down to my attack host, and down to what the input value is.
Right.
Basically, the whole strength of the full disk encryption relies on the user, which is not good news. Because what you just told me, if you have this on your smartphone, I pay you a beer.
Oh, you can pay me a bit. Well, it's free beer anyway, right? So. but
you're absolutely right.
Right.
It's down to the password. I have a very dear colleague at work who says, get rid of the passwords. Yeah, I agree with you, get rid of the passwords, but bring something better. Right. Because I also looked at the face unlock, which is terrible.
Yeah. And I guess my second question is, I mean, because this kind of goes into that entire discussion, the FBI versus Apple, where they try to brute force the Apple, because this was exactly what they're asking for from Apple, right? What else do you think iOS does better than Android in that respect? And I'm not an iOS guy, I'm just curious if you looked into it.
Yeah, I'm not an iOS guy as well. I had a short look at it. When I understood it correctly, iOS does more than just full disk encryption, it does a file-based encryption. And actually in Chrome OS, I saw also some signs that they want to build in that, or maybe they've already done it and I missed it. It's certainly, because of the lack what full disk encryption is, you need to shut down the device. We use smartphones. I never shut down my smartphone. I reboot the smartphone. So the full disk encryption is never really working for me. What we need is a device encryption plus file-based encryption. If you only have file-based encryption, we still give away information in the metadata, which also NSA, FBI, and everyone loves. And I'm not against law enforcement. Actually, I was fortunate to talk to the lead prosecutor of the Canton of Zurich for my master thesis. And even he is on the point to say, let's use device encryption. Use encryption, please, use it, do. It's also the crooks that use it, yes, but they also use the bad stuff to make you hurt, to make you bleed. So use it and secure yourself. We have to deal with it, yes. And there's a second trigger point why I started this topic, one of which was the improvement that Android said and the release of full disk encryption out of the box. And the other one was, I think his name is Comey, the FBI director, who said, we're going dark. And I want to look at it. Are we going dark? And yeah, no, not so much, right? At least not with Android. You still have options. And yes, brute forcing takes a hell of a lot of time and a lot of processing power, memory power. It does. It's complex, but it's still possible.
You said that 128-bit AES key is generated on the first boot, and you hinted that it wouldn't be the best idea. Are you aware of any research done looking into the entropy, the effective entropy of the AES key?
That's the point. No, I'm not aware of that. I have this point in my thesis as future work. Feel free to start on that. But think about it. What is DEF-U random? It's a random number generator, and it never blocks. And it's not just the twice 16 bytes that read from DEF-U random. If Android starts up, every canary that protects against memory corruption is read from DEF-U random. So I have the idea that probably the entropy of the key could lack because of that, but I didn't know analyze this. You need a device to do that. You cannot do it on a virtual machine because it reads from the hardware. And I didn't want to destroy my phone because what you have to do basically is reiterate the full disk encryption initiation process. And that writes a lot of time on your flash memory. And as we all know, SSD flash memory doesn't like a lot of writes all the time. But the issue is, DEF-U random, if you shut down, it writes the entropy into a file and reloads it. But that file doesn't exist on the first boot, if I'm not mistaken. So have a look at it.
I presume that a time measurement of 2 hours includes the scrypt computation of the client. Is that correct?
Yes.
So how much faster could you get if you could pre-compute the first iteration offline, then get all the signatures at once, and then continue on the PC? I mean, how much faster would it be? I mean, I'm asking about the time, minimizing the time you actually need access to the device.
Yeah, you're right. It's a good point. It's a valid point, and it's something how you could improve the brute force strategy. You could start with essentially creating an intermediate key dictionary on the attack host and send over the whole dictionary to the device and ask to sign them. What else we could do is run the attacks in parallel and increase my POC server script to take on more connection. It could also already help.
I mean, can you make an educated guess? Would
No.
it be minutes? Would it be
No.
seconds? No. You don't?
Yeah, well, no, I don't want to make an educated guess because I can't.
Okay.
I'm more of the person I would try it out and see.
Okay. I mean, if it took minutes, are you able to restore the device to a usable state after running the attack?
I mean, it's at the end, it's writing back the image, right? So I would say yes.
Okay.
You think about the evil maid attack or something similar.
No. No.
No, it's a good point. And it's
I mean,
exactly
you would probably need twice, because you first need to steal it from me for a few minutes to take the images and salts and stuff. Then you can pre-compute your tables. Then you wait until I have lunch or something, steal it again, run your attack.
Yeah.
The question is, how much time would you actually need?
that scenario is actually even better. If the user has already a SU binary on the phone, all you need is an application that allows you to connect to the phone. You can give it back to him and you never have to go back to the device.
Okay.
You just need to be able to get on the device and run the SU script. And
Okay.
let's try it out, I would say, but I cannot make a guess.
Okay. Thank you very much. I'm going to